Now, a receiver operation, so we will consider that a probability of error, and we can say that when we say that a 0 is transmitted or 1 is transmitted, so when this 0 and 1 is transmitted, even if a 0 is transmitted, we will get that output is high, so that's the probability of 0. And we 1 is transmitted, we'll get that value below threshold value, that is probability of 1 P1 of V. So these are about the P of 0 VTH and P1 of VTH here. Now from this, we can find out what will be the bit error rate. So we say that a probability of 0 or a probability of 1 is transmitted. So means occurrence of that bit A, generally we say that A is equal to B is equal to 0.5. Earlier we say, means we have the a probability of P is equal to what? A P1 VTH plus B P of 0 VTH here. So now this equation, this A and B is equal to 0.5, then we can write that P0 of VTH is equal to P1 of VTH is equal to 1 by 2 PE. That is called as a PE is called as a bit error rate or a error probability. Now from this we can write here bit error rate P of Q. Q means what? That is about a on and off timing for this bit here, or that is nothing but we can say here what are the exact location or evaluations for this particular bit here. So P of Q, okay, will is equal to 1 by pi root of pi here. That Q by root 2 is equal to infinite here, e raised to minus x square dx. So we can write again simplified 1 by 2 1 minus ERF error function Q by root 2 approximately equal to 1 by 2 pi into e raised to minus q square by 2 by. So Q is saying about that what will be the on and off period, or this Q can be defined in terms of VTH minus V off when we have the variance sigma off, or V on minus VTH when we have on data, that's about Q, or equal to V on minus V off divided by sigma on plus sigma off. And the error function ERF of x is equal to 2 by pi 0 to x e raised to minus y square into dy. So you will specify the performance of a receiver because we say that it is defining the level. So that's why Q will specify the receiver performance, and that receiver performance can be expressed with respect to the what will be the bit error rate BER. So we can write here a probability of error, or we can say that a BER with respect to a Q value. So now that graph is reflecting here with respect to that a probability of error, that is a P and a value of a Q here. 9 10 to the power minus 6 3 10 to the power 0. And this one is about 0, 2, 4, 6 and 8 here. So now this 10 to the power minus 15 minus 12 9 6 3 and 0, and this is about a 8 here. So we'll get that a plot of a probability of error versus Q, it will be likewise. That is about a plot. So means we can say that for a Q is equal to what? A 5.99781, then probability of error is equal to 10 to the power minus 9. So now this one. For this graph, the Q value according to that we'll get that a bit error rate. So this figure shows that a bit error rate, that is PR, P or BR here, probability of error or a BR with respect to that value of a Q here. This is about a Q. This one is about a probability of error. So what value of this Q, according to that we'll get that a probability of error. So that will be defined by this particular graph here. Now if you consider that variance we consider, that is sigma on is equal to sigma off is equal to a sigma. So it can say that a B of is equal to 0 if supposed to be considered that in that case B on is equal to 1 V. So then a threshold value of voltage, that VTH is equal to V by 2. For this particular threshold value of voltage, Q will be what? V by twice of sigma. Now this one, okay, this equation we saying that a Q and all, so we can find out a Q is equal to T sigma. Then in that particular case, probability of error, when we can say that sigma on is equal to sigma off, that is equal to what? 1 minus error function B by 2 under root 2 sigma. That is about a probability of error here. Then we can find out what will be the BER for this case. So BR for this case, so again we can consider that 10 to the power minus 6, minus 5, minus 4, minus 3, 10 to the power minus 2, 10 to the power minus 1, and then 10 here, 1 here. So according to that, we have this p by 6 here. So it is 0, 2, 4, 6, 8, then 10, and then it is about it. Maximum 10 to the power minus 12, minus 11, likewise. So this is about your PR here, and this is about it V by 6. So this graph, we can say that sigma on is equal to sigma off when V off is equal to 0. So curve will be likewise. So this is a graph for this BR with respect to this one. But in the case of a V, if supposed to be V by 6 is here, V by sigma, not 6, V by sigma is here, that is variance. And then we can say that this one is a 10, 12, 14, likewise. So in that case, V of sigma will be likewise. That is about a graph here. Means from this particular case, if we consider that V by 6, if it is a increasing here, then a BR will be decreasing here. Okay, from this graph, we can say that BR will be decreasing when V by 6 will be increasing here. So means we can say that if that signal to noise ratio is small, then we can say that a error rate BR that will be a tolerable. And if it is the signal to noise ratio, if it is not a narrow or a small, then bit error rate is not acceptable here. So that's why that bit error rate or that error occurs will be more here. So that's why BR is not acceptable. So for that purpose, to get that BR within that particular range, so we need to define that a threshold value appropriate or threshold level appropriate so that a signal to noise ratio can be appropriate there. So means performance of a receiver, we can say that it is defined or a transmission link. When we design a transmission link, then the performance of a receiver, that is depending upon that a bit error ratio, and that bit error ratio is again depending upon that threshold value or threshold level in which we can define the or in which we can obtain the signal to noise ratio. So with this we can say that a bit error rate is one of the performance measure or a performance requirement for the transmission link. So this is about, we can say that BR is a one of the component for the receiver for the performance requirement. So if we consider that a network, so what will be the BER? So generally we say that a BER is about 10 to the power 9 minus 9 to the 10 to the power minus 12 for the optical communication. If that BER is greater than that, then performance of your system degrades here. So that's why to achieve that a particular BER bit error rate at a given data rate, so we need to specify what will be the optical power level is to be received, or what will be the optical power that will arrive at this particular detector, so that a detector will receive, or your receiver will receive that particular minimum power level, and that is nothing but the a receiver sensitivity. So value of that particular minimum power level that will be received by this receiver or detect by the detector, that will be called as a receiver sensitivity. And a receiver sensitivity is depending upon that what will be the optical power incident on the detector there. Means we can say that power incident on detector. So detector is what? A pin or a body. That is a photo detector. Otherwise, you will take a different way here. So it is incident power on this photo detector. So according to that, we can find out the receiving sensitivity. And that receiver sensitivity will give what will be the minimum power required, so that we will get, or that detector detect that particular signal there. So means if photo detector output, that will be depending upon that what will be the incident power level. So that is about a receiver power or receiver sensitivity gives a measure of a minimum average power that is required to maintain that a BER. Maintain the BER means what? Worst case of a BER at a specific data rate. So means for a given particular system, when we can say that a 1 and 0 pulses are transmitted. So if it is 1 transmitted, current will be I1. If 0 transmitted, if we say that a 0, I0 is the current, and their corresponding noise variance will be a sigma 1 and a sigma 0. If we assume that there is a no pulse, no zero pulse, okay, there is no zero pulse, in that case, Q is equal to what? I1 minus I0, that is general equation, sigma 1, sigma 0. If there is a no zero pulse, then it will be what? I1 by sigma 1 plus sigma 0. This is about a equation. If there is a no zero pulse, no zero pulse means what? I0 will be 0. No zero pulse means what? I0 is equal to 0 when there is a no zero pulse. So that's why I1 by sigma 1 plus sigma 0. And then we can calculate that a receiver sensitivity with respect to what will be the bit period is equal to what? P1 by 2 equal to I1 by twice of Rm here. Okay, equal to Q sigma 1 plus sigma 0, that is variance, divided by twice of Rm. And this R is nothing but what? A unity gain responsivity, and this M is equal to what? Gain of the photodiode. So now the receiver sensitivity is depending upon that whatever the noise present. So noise is present, generally there are the thermal noise and a short noise. The thermal noise, if there is a at a load, and a short noise when a light falls on the detector, so according to that a short noise will be generated. So that's why the thermal noise is depending upon the whatever the load register, and a short noise is a process of the statistical noise. If there is a light, so short noise, and a current is detected because there is a thermal variation across this load, so that's why a thermal noise there. So now we consider that that particular noise, short noise, is again we say that it is depending upon that received power, because electron hole pair generation, it is in a random or a random fluctuation process. So that's why there is a short noise there. Now, if you consider that the short noise variance for a one pulse, and there is a no received zero pulse is there for the 0 and 1 pulses, because if there is no optical power, in that case a variance we can say that sigma 0 is equal to sigma t square, and a sigma 1 square is equal to what? A sigma t square plus sigma short square. And this one is about a variance for the noise. This is about sigma t is for the thermal noise, and sigma t and sigma short. This is thermal noise, and this is about a noise variance for this short noise. So in that case, if there is a pulse, sigma short is equal to what? A TQ, that is R P1 M square F of M PE, or we can write here 4Q R, then AP sensitivity into M square F of M P by 2. And that F of M is nothing but what? A noise figure for this photodiode. And this B is nothing but a bit rate. B is a bit rate. And that bit rate is depending upon that what will be the receiving bandwidth. So that's why B is equal to what? B by 2. And a thermal noise, sigma T, or thermal noise current is about, we can say that because of the thermal noise there is a thermal noise variance 4 kb into T by load resistance RL with respect to whatever the noise figure function for the amplifier into a P by 2. Then by substituting that sigma 1 is equal to what? A sigma short plus sigma T square raised to 1 by 2, and the sigma 0 is equal to sigma T in that receive sensitivity equation. Then we'll get that receive sensitivity is equal to what? 1 by R, that is Q capital M, then F of M to BQ by 2 plus sigma T into your Q by capital M. That is about a sensitivity. Okay, that is about a receive sensitivity. And we stop here and we'll see that what will be the a quantum limit, or what will be the minimum power level required for this particular receiver there.